Hello, and thank you for joining our presentation about the efficient tiling of point features into 3D tiles with support for discrete LOD. First, we will talk about our motivation behind creating a new generator for 3D tiles. We explain some of the technical backgrounds, the implementation itself, how we evaluated the implementation against other generators, and conclude the presentation with a discussion and an outlook. An increase in the collection of large-scale geospatial datasets in recent years strains traditional methods for storage, processing, and visualization. 3D Tiles is a method that allows streaming large-scale, three-dimensional geospatial datasets efficiently on almost all devices. In addition to that, 3D tiles also allow real-time user interaction, which increases the fidelity of rendered scenes. However, it's currently not possible to directly stream point features as 3D tiles. The generation of 3D tiles usually requires intermediate 3D models, which are often time-consuming and costly. Procedural models, on the other hand, can reduce time and cost, but even those are often inflexible and not practical. For that reason, we are looking for a method that directly tiles point features into high-fidelity, large-scale 3D tile sets, and to further increase the performance of these tile sets, we also desire discrete level of detail support. 3D tiles are an ideal candidate to achieve that. 3D tiles were originally developed by Cesium, but have since been adapted as an Open Geospatial Consortium standard. 3D tiles combine efficient rendering and storage methods to render high-quality results. In addition to that, 3D tiles support a wide variety of geospatial formats, among those meshes, point clouds, and both batched and instance 3D models. There are already several different applications out there that can be used to generate 3D tiles from geospatial datasets. One of these applications is Cesium Ion. It's a cloud platform provided by Cesium. However, it requires intermediate models, and it was not successful in creating the large-scale 3D tiles that we desired. On the other hand is SafeFME. SafeFME can read different file formats, for example, point features, shapefiles, file GDBs, and 3D models, augment these datasets, and then generate batch 3D tiles. However, due to the large number of features in our scene, it's not ideal to have batch 3D models. The by far most promising solution is i3DM Export. It reads features from PostgreSQL databases and generates tile sets directly based on those features. However, it requires the data to be prepared with scaling, the models, and so on in the database itself, which is not always practical. And due to other limitations in the application, it cannot always prevent repetitive patterns in the dataset for densely clustered features, and there's no support for LOD. So it works well for point features, for individual point features, but not for densely clustered point features. In addition to that, since the tiling is based on the number of features and not on the location of the features, changing the dataset would require a complete regeneration of the tileset. We aim to overcome these limitations with our own implementation. Our implementation does not require intermediate models. It only requires limited preparation of the data. It supports discrete LOD, and it applies a tiling method that is predictable and calculatable, which allows the partial recreation of the tile sets. Our solution was successfully tested with our 2.8 million point features in a realistic forest inventory dataset. The data processing of our application can be split into multiple different steps. The first step among which is the data retrieval. We are currently capable of reading the point features from several different sources, among those CSV shapefiles and PostgreSQL databases. The data from these sources must include the geospatial coordinates, and several attributes, among those the feature types and the dimensions of the features. Since we are using it for force inventory datasets, we are currently requiring the tree height and the crown area of the trees. All these parameters are then converted by the application into a common format. So for the coordinates, we utilize UTM, which helps to massively simplify further processing, and for the attributes, we utilize meters. Using UTM coordinates over other coordinate systems allows us to immediately apply our tiling methods, but we achieve a tiling by dividing the x and y coordinates of the point features by a constant d. D is parameterized by the user and is the dimension in meters of each tile. And by applying this formula, we achieve a tiling approach that is completely independent of other features in the same tile. So if you give us a point feature, we immediately know in which tile it belongs. Once we know in which tile each point feature belongs, we can start preparing the models. For each feature type and for each LOD, we expect an individual GLTF model. The complexity of this GLTF model is irrelevant for the application, but has a significant impact on the later performance of the visualization. However, the size of the model, so the dimension of the model, is irrelevant for the application, since we retrieve the dimensions from the model file and then apply a scaling in accordance to the formulas seen in the slides and to the attributes of each feature, which in our case is the height and the crown area of the trees. This formula is applied to each individual point feature. So for each point feature, we have an individual scaling. While the individual scaling of the point features already solves most of the issues with repetitive patterns, it cannot solve all of them. To prevent all repetitiveness from the scene, we apply a certain degree of randomization to the rotation of the models. We apply a random rotation around the y-axis of 360 degrees, and we apply additional tilt around the z and x-axis of up to 7 degrees. After we apply the randomization, we calculate the bounding volume of each feature point and its model. The bounding volumes later has the visualization to decide which features to display and which features to omit from the visualization. The more precise this bounding volume is, the more precise the later bounding volumes of the tiles can be, and therefore the better the performance of the visualization. After we prepare the models, we continue with an optional step. Since there might be slight differences between the elevation data in the dataset and the actual digital elevation model that is used for the visualization, we allow the retrieval of the elevation from the digital elevation model that is later used for the visualization. This prevents floating features in the scene and can massively improve the fidelity and the realism of the scene. 3D tilesets consist of several levels of tiles. The tiles at level 0, so the lowest level, must have at least one point feature to be generated. The tiles of higher level must have at least one child tile, so one tile of a lower level, and at most t-squared tiles. T-squared is another parameter of the application which allows controlling of the tiling procedure. By utilizing a variable t, we are not limited to quadritiling, and in further tests it was shown that t of 3, so 9 child tiles per tile, had the best performance. During the tiling, the features or the tiles of the lower level are assigned to the higher level based on t, until there's only one tile left at the highest level. For each tile, based on the features or other tiles that are contained within, a new bounding volume is calculated to control the visualization. The application of this tiling approach ensures a predictable and calculatable tree structure. At this point, we have the logical structure of the tileset within our application, but it's not yet written to the hard drive. Each tile at the lowest level, so at level 0, consists of a JSON file and an i3dm file. i3dm files stand for Instant 3D Model Files. They are part of the 3D tiles definition. i3dm files store a reference to a GLTF model, the position of the feature in an Earth-centered Earth-fixed coordinate system, the scaling and the normal up and the normal right vector. For that reason, we require for each feature type and for each level of detail for each feature type an individual i3dm file. And those i3dm files are then combined using the JSON file. At every higher level than that, the files only consist of JSON files, since we don't have any models at the higher levels. A JSON file stores a reference either to an i3dm file or to other JSON file, and each of those references has a bounding volume that controls the visualization. In addition to the bounding volumes, each of those files also have a geometric error. The geometric error is mainly responsible for deciding when to start displaying features and when to replace a feature of a lower LOD with a feature of a higher LOD and vice versa. To visualize the relationship between the files and the features in the scene, we can have a look at these figures here. We see at the lowest level we have i3dm files, and then the blue area around it, basically a JSON file. And then at a higher level, we get additional JSON files with a combining outer JSON file. And then at the highest level, we get the same thing again with the final JSON file. The video playing on the left side of the slide showcases the behavior of our discrete LOD support. As we zoom into the scene, the models of the lower level LOD are replaced with models of the higher level LOD. And as we move through the scene, we see that this is continuously updated when we move to new areas. The tilesets generated with our methods were compared to several other generators, among those i3dm export, FME, and CCM ion. The first couple of tests were mainly focused on finding the optimal parameters for all generators to have a fair and educated comparison for the later dynamic test that benchmarks the performance, the visualization performance of the different generators. This dynamic test took place on an forest inventory dataset of the Elliott State Forest in southwestern Oregon. This forest inventory dataset contains 2.8 million point features, has 3 different tree species, and is a state-of-the-art forest inventory dataset. Since both safe FME and CCM were incapable of generating a 3D tileset with 2.8 million point features, the test took only place between i3dm export and our own method. And since i3dm export does not support LOD, we prepared 2 different tilesets using i3dm export, one with a higher level LOD and one with a lower level LOD, while our own tileset combined those LODs into one dataset. This graph shows the result of the dynamic performance test. We took a flight over the 3D tileset in the browser and recorded the average FPS per second. As you can see, our own method achieved an average frame per second of around 48, while the i3dm export with the lower quality model achieved around 34, and the i3dm export tileset with the higher quality model achieved around 18 frames per second. So we can see that we have a massive improvement of the performance. And I would like to point out some specific areas of the in the graph. You can see in the center that suddenly all frames per second jump up to 120 FPS. This is based on the terrain at this certain location. There were just not enough trees nearby to start rendering them, and as such, there was basically an empty scene, and it went to the maximum frame per second. However, you can see that both I3DM tilesets started not rendering something much earlier than our own proposed solution. So not only does our tileset show much better performance by increasing the distance of the displayed features, it also increases the fidelity in the scene. So let's summarize. In this presentation, we presented a new method for tiling point features to 3D tiles without the requirement for intermediate models, and we achieved an excellent performance, especially for densely clustered features and large number of different feature types. In addition to that, our own method provides several advantages over other generators. For example, we have the support for level of detail, for discrete level of detail. We do not need to adjust or augment the incoming data set, and we have a calculatable and predictable tile structure. Despite the fact that we already achieve excellent performance, there are several things we would like to work on next. First, we would like to update our tiling method to support the latest version of the Open 3D Tile standard. And we would like to implement the partial update of the 3D tiles fully. At the moment, there's a proof of concept, but we would like to finish implementing this. That concludes our presentation. Thank you for your attention, and if you have any questions, I'm available in the chat. Thank you.